One of these is this particular equilibrium here. We take the copper 2 plus. Now, if we add a little bit of ammonia, we end up getting a precipitate. Did you get a precipitate when you added the ammonia initially?
Yeah.
Okay, that precipitate is copper 2 hydroxide solid. It's a light blue precipitate, and then we'll form 2 ammoniums here. So this is the reaction that happens. If you add a lot of ammonia, what happens is we'll have a competing reaction. This is actually metathesis. Even though this doesn't look like a metathesis reaction, it is. If we add excess ammonia, that is, if we add concentrated ammonia here, we end up getting something else. Now with the concentrated ammonia, we're going to get 4 NH3s, and then we end up forming this, CuNH3 for 2 plus. The tetramine copper 2 ion. Okay, this is the dark blue stuff. So we have this complex equilibrium. This is a light blue precipitate. This is a light blue solution. This is the dark or the deep blue solution.
I have no idea where we are.
Number A, or I guess letter A. Letter A, this doesn't, when we're looking at A, part 1A, part 1A deals with this equilibrium here, the copper 2 plus plus the 4 ammonia. But there's one more reaction happening here, and the one more reaction is this formation of the light blue precipitate. And so initially when you add the ammonia, you add a little bit. When you add a little bit of ammonia, you get a light blue precipitate. As you keep continuing adding the ammonia, that precipitate dissolves and forms this dark blue solution. Did you observe that? Yeah, actually that's what you should have observed, except the light blue precipitate wasn't shown in there. And so what I'm showing is this, the formation of the light blue precipitate before you did the complex formation. Now, this is distillate too, because here, if we remove the copper 2 ion using concentrated ammonia to form the main complex, all that precipitate dissolves. So you precipitate it and then dissolve it. That's what should have happened. Now, I wanted to talk a little bit about this particular reaction here. This is a metathesis reaction, and it's because of ammonia. Ammonia is a weak base, and weak bases are weak electrolytes. And weak electrolytes do what? Well, weak electrolytes partially ionize, partially dissociate, but bases don't do that. What do bases do? You know, bases don't ionize, like ammonia doesn't ionize, and bases don't dissociate. Instead, bases do this. Bases hydrolyze, that is, they react with water, and they do partial hydrolysis of water. And what we're going to form here is ammonium and hydroxide. And so weak bases partially hydrolyze water to produce a little bit of hydroxide. Strong bases completely hydrolyze with water to form lots of hydroxide. And so the difference between a weak base and a strong base is the amount of hydroxide that's produced. In this case, what we see here is we're going to have 99.9%, greater than 99.9% of this at equilibrium, and then less than 0.1% of this at equilibrium. And so we barely form any of the ammonium and the hydroxide ions. Well, in other words, the amount of hydrolysis is pretty small. But it turns out that the amount of hydrolysis that we see for this is big enough to precipitate out the copper. And so when we have the ammonia in the water here, we have 2 ammonias, 2 waters. It's going to form 2 ammoniums and 2 hydroxide here. And so the little bit of hydroxide that forms in the base hydrolysis with water is enough to get this light blue precipitate. Now you might ask, why don't we just go ahead and write ammonium and hydroxide here instead of ammonia and water? And the reason is when we write an equation like this, we want to write it with the chemicals that we actually go buy. So if you want to go buy some, let's say I wanted to buy some ammonium hydroxide. So I go to the chemical store to buy some ammonium hydroxide. I get the bottle of ammonium hydroxide. I bring it home, and then I analyze it. When I analyze it, I see I only have 0.1% ammonium hydroxide, 99.9% ammonia and water. So what do? I return it because it's not the stuff I wanted. I wanted the ammonium hydroxide, and I got ammonia. So I return it, and they give me a new bottle. But you know what the new bottle is going to have? The same thing. And this is the equilibrium. The equilibrium is heavily favored towards ammonia and water. And so we don't write ammonium hydroxide here, even though it is ammonium and hydroxide that react. We write the chemicals that we purchase. And the chemicals that we purchase would be aqueous ammonia. From that aqueous ammonia, we get a tiny, minuscule amount of ammonium hydroxide, and it turns out it's enough to get this light blue precipitate. As we continue adding ammonia, though, that precipitate's going to disappear. So this is, even though this does not look like a metathesis reaction, it is a metathesis reaction because we do get a small fraction of ions, and this small fraction of ions is enough for precipitation. Hydroxide, most hydroxides are highly insoluble, and so that works. There, sorry. So now, if I don't want to lose this precipitate, then I shouldn't use ammonia. So for example, if I use copper 2 ion plus hydroxide, then I'll have no problem. Here. So if I want more copper 2 hydroxide, I just use Le Chatelier's principle. I'll keep adding more and more hydroxide, make it more and more concentrated. The more concentrated the hydroxide is, the more this shifts to the right. It's Le Chatelier's. So if I don't want to lose this, I can add excess hydroxide and nothing will happen. I'll just get this light blue precipitate. If I add ammonia, then I have competing reactions. The competing reactions are this metathesis reaction versus this Lewis acid-base reaction. Eventually, who wins? The Lewis acid-base reaction wins because it turns out this complex is quite stable. And so that's why it wins. Now, this complex formation, how do I know it forms a tetramine copper 2 complex? How do I know is I look it up in a table, and a good table is Appendix D in our textbook. Appendix D has a long list of complexes that form. So I know here, if I add excess hydroxide, I'm not going to form a complex. However, if I try to do the same thing with aluminum, that would result in a problem. So if I have some aluminum, and I wanted to precipitate out the hydroxide, I'd add 3 hydroxides for every aluminum. I'll get a white gelatinous precipitate of aluminum hydroxide. Now I want to apply Le Chatelier's principle like I did here. Increase the hydroxide concentration, shift right, get more precipitate. I try to do the same thing here. Increase the hydroxide concentration, shift right, get more precipitate. That's what I'd like to do here. Unfortunately, what happens is if I increase the hydroxide ion concentration, the precipitate starts to disappear. And the reason the precipitate starts to disappear here is because if I just bump it up 1 extra hydroxide, I will form this. And this is the tetrahydroxyl or hydroxido aluminate 3 ion. And so what happens here is this. Le Chatelier's isn't going to work here because with hydroxide it's not going to work because as I increase the hydroxide, what's going to happen is the hydroxide is going to complex with aluminum to form this, which is a aqueous ion. Whereas over here, hydroxyl complexes of copper, no, there aren't any. And so I can increase it here without any problem and just maximize the precipitate. Over here, I can't increase it. And so we have to worry about these types of things. So that's why we have to be aware of other reactions that could occur. And for Lewis acid-base reactions, those we can find common complexes in Appendix D of our book. There's other ones as well that we have to worry about. For example, if I'm trying to precipitate a silver ion, I can use chloride. If I use excess chloride, then that should shift it to the right more. So Le Chatelier should work. However, if I try to precipitate out lead, I'd want 2 chlorides, and I'd form a white precipitate of lead 2 chloride. If I want more precipitate, then I should add more chloride. Right? Increase the chloride, I'll precipitate out more lead, right? However, I look in Appendix D and I see a problem. In Appendix D, if there are 4 chlorides, what's going to happen is I'm going to complex this. Actually, something like that. If there are 4 chlorides, I'll complex it like this and get this tetrachlorofluoride ion. Now, what that means is this. That means if I continue adding more and more chloride, this precipitate is going to disappear. The reason is with the right amount of chloride, I got PbCl2. With excess chloride, I'm going to go down this alternate path where I'm going to have complex formation. And so what's going to happen is the precipitate is going to form and then it's going to disappear as I continue to add chloride. Here, the same thing. The precipitate forms and then will disappear if I continue to add chloride. And so typically what we do is we keep a close eye on it and we try to maximize the amount of cloud formation. And then stop when we start to see it disappear or when there's no more change. All right, so those are some more complicated observations on this particular lab. What was the other lab that we did last week? Yeah, the hydrolysis pH lab, but we did it different. We changed it to determining K and then determining the pH based on, or so using K for stoichiometry. And so for that particular lab, there's no report sheet. You know, for this Le Chatelier's, there's a report sheet you'll turn in. For that lab, just maybe take a scan of your calculations that you did. You know, using like Genius Scan or Cam Scanner or something like that, and then you're going to submit that online. I just want to see the calculations. That's it. So that's fine. Just take a picture of what you did. However, I did want to talk about the calculations. When we did the calculations, I made an assumption there. I simplified the calculations. And let me talk about how I did that. Whenever we do like pH, like we did a pH measurement, the pH measurement measures the total hydronium concentration at equilibrium. And what I did in that calculation was I assumed all the hydronium came from ammonium. But that's not true. All the hydronium does not come from ammonium because there is one other contributor. The one other contributor is we call KW. KW. What KW is when we look at water at room temperature, and look at its energy distribution, we see some kind of curve like this. So this is pure water, and we'll do at 25 degrees C. Pure water at 25 degrees C is going to have an energy distribution that looks like this. And it turns out there's a very small population of high energy water molecules way out here. So with this high population, I mean not high, high energy, small population, what that can do is it can undergo a violent collision. And so I have two water molecules. If they collide violently with the correct orientation, then what can happen is a reaction, the Bronsted acid-base reaction. So one hydrogen gets knocked off and taken by the water, leaving hydroxide here. So in other words, we can form some hydronium and hydroxide. Now, these have to be very energetic molecules because, you know, when we compare the acid, hydronium is much stronger acid than water. Hydronium is strong acid. Hydroxide is strong base. Water is not. And so we're going from very weak acids and bases to very strong acids and bases. So this is very uphill in terms of energy. Hydronium and hydroxide are high energy, very reactive acids and bases. Water, low energy, very unreactive acids and bases. And so what we're looking at is, you know, what fraction of this population can make it up this steep climb here, the long climb uphill. And it turns out it's very small. So if I had a billion, a population of a billion, which would be the area here, how many could make it up? Do you know how many could make it up if I had a billion water molecules? Well, actually only 4. 4 out of a billion. Well, 4 out of a billion, is that much? No, barely any. But in Chem 1B, we care about that, and then we're going to determine that. Now, how can we determine that? Well, all we do is we take some pure water, and then we could just do the same thing we did in lab. That is, in the pure water, H2O liquid and H2O liquid, those are pure. The concentration doesn't change. The activity is just 1. And initially, what we can just do is we can just pretend nothing's happened yet. So let's say it's frozen, and there's no collisions. And then what I do is I'll just unfreeze it to 25 degrees C and then let it collide. So some of these are going to make it up. And how much? Oh, I don't know exactly, so I'm just going to call it plus X molar and plus X molar here. So that at equilibrium, I'm going to have X molar hydronium and X molar hydroxide. So for every hydronium that forms, I form 1 hydroxide. And then I'm going to measure the pH. Do you know what the pH of pure water is? A lot of people have it memorized. The pH of pure water is 7. Yeah. And so we measure the pH, and the pH is 7.00. How many sig figs is that? Well, it looks like 3, but in reality it's just 2. It's 2 because this is a power function. And so for power functions, the sig figs come after the decimal, so it's only 2 sig figs. So that would be the pH. Well, it's the power. pH is the power of the hydrogen ion concentration. So that means the power of the hydrogen ion concentration is 7. That means the hydrogen ion concentration, or hydronium concentration, same, is equal to 10 to the minus 7.00. That would be the power, molar. And then I'm allowed 2 sig figs, so I'm going to add those here. I'm going to call it 1.0 times 10 to the minus 7 molar. If I punch it out in my calculator, that's what I get. So the power of the hydrogen ion concentration, actually it's the negative power because the power is minus 7. And so do the negative. And so from the pH measurement, we see the concentration of hydronium is 1.0 times 10 to the minus 7 molar. What would the concentration of hydroxide be? The same. Now, for every hydronium, I need to form hydroxide. So this is the hydrolysis of water by hydrolysis. It's the autohydrolysis. And we can get the equilibrium. This is at equilibrium because the pH measures the equilibrium concentration. And then we could get K for this reaction. K for this reaction, just do Kc, is going to be equal to the hydronium ion concentration at equilibrium times the hydroxide ion concentration at equilibrium. And so this is going to be 1.0 times 10 to the minus 7 times 1.0 times 10 to the minus 7, which equals 1.0 times 10 to the minus 14. And we call this Kw. Kw. It's just Kw is water self-reaction, water auto reaction, water auto ionization, water auto hydrolysis, whatever you want to call it. And Kw is a constant at 25 degrees C. At 25 degrees C, we're going to have that population here that has sufficient energy to make it up the hill. What happens if we change the temperature? Let's say I increase the temperature. If I increase the temperature, what happens to this curve?
It changes.
In what way does it change? Well, the area under the curve stays the same because let's say, you know, I have 1 billion waters or whatever. So the area, but it gets lower, but it spreads out more here. So it flattens out and then grows here. In other words, it kind of shifts to the right curve. So if I increase the temperature, the population grows. If the population grows, then I'm going to get more collisions. More collisions is going to lead to more hydronium and more hydroxide. And if I increase the hydronium and hydroxide, the pH changes. And so the pH of pure water at 25 degrees C is 7. However, if I increase the temperature and this goes to, let's say, 10 to the minus 6, 10 to the minus 5, what happened to the pH? The pH went from 7 to 5 to, or 6 to 5. In other words, the pH goes down. So as the temperature increases, we generate more acid and base, and therefore the pH goes down. But it's still neutral. And so even if this went to 10 to the minus 6, it's going to be 10 to the minus 6 here and 10 to the minus 6 here. And the way we define a neutral solution is a neutral solution is going to have the same amount of acid as it has base. And so even if we change the temperature and we change the amounts here, it always stays neutral because we always have the same amount of acid and base. So at higher temperatures, we're going to have a lower pH. At lower temperatures, this curve shifts to the left, and we'll have a higher pH. But it stays neutral. So what that means is the pH is kind of complicated, and old pH meters, you know, it depends on what the temperature is. You know, the pH for pure water depends on what the temperature is. But nowadays, we don't want to hassle with that. You know, what's the temperature today? Temperature today is 21 degrees, 21.0 degrees C. Is the pH of pure water going to be 7? No. In fact, the pH of pure water, it's a little cooler. Therefore, we're going to get less. If we get less, then we might get like 10 to the minus 8. If we get 10 to the minus 8, then the pH is higher. You know, it would be 7 versus 8. it's kind of inverted, it's flipped because of the negative sign here. pH is positive, whereas the concentration is negative in this case. So what we do is we use a pH meter, a modern day pH meter that has temperature calibration in it. And so what it does is it constantly offsets. If it's 21 degrees today, then it'll measure the water as pH 7. You know? And if the temperature increases, then it'll adjust it automatically to compensate for that. And so nowadays, when we think of pure water is always pH 7 because our pH meters can adjust to the temperature, and we just want to have water at pH 7. It's easier to deal with in that sense. So what happens is if I add acid to the water, then the hydronium increases and we shift it to the left. And so that complicates things because if I have an acid, there are two sources of hydronium. The hydronium is going to come from the acid itself, and then there's going to be hydronium from Kw, from water, because you can't stop the water from colliding with one another, water molecules from colliding with one another. And so what I did in class wasn't completely accurate. And so let's look at an example of this using it in a solution. Actually, let me do it over here. So the pH, when we measure the pH is the total hydronium at equilibrium. When I did my calculation here, I set up an ice table here. And so we did this. We had ammonium plus water. This gave us hydronium plus ammonia. And so I did the initial, which was 0.10, actually it was just 1 sig big, 0.1 molar. Water is pure liquid, 0 molar and 0 molar. So we started off with 0.1 molar ammonium, but ammonium is a weak acid, and weak acids hydrolyze water, partially hydrolyze water. And so this is going to hydrolyze, but I don't know how much, so we're going to call it minus X, plus X, plus X. And then at equilibrium, I'm going to have 0.1 minus X molar, X molar here, and X molar here. And then I measured the pH. What was the pH? .18 was the average? Okay. So we measured the pH. pH is came out to 5.18. And therefore the hydronium ion concentration is 10 to the antilog, 10 to the minus pH molar. The pH is, and this is 10 to the minus 5.18 molar, which was equal to what? 6.61 times 10 to the negative 6 molar.
Yeah.
Okay, and then what did we do? We plugged that in here. We said that, okay, this is the hydronium ion concentration we measured at equilibrium. And then we plugged it in here, and we calculated our K value. Do you remember doing that? Okay. But technically, this isn't 100% correct because I'm ignoring another source of hydronium. Can you stop water molecules from colliding at 25 degrees C? No, it's impossible. The water molecules are going to continue to collide. If the water molecules continue to collide, I shouldn't do this because this is the total hydronium. This is the total hydronium. And I'm assuming all the hydronium came from the ammonium. That's not accurate. Some of that hydronium came from water.
Professor, I meant to say 6.61.
Okay, 6.61.
I just said it wrong. 6.61.
Okay, all right, thank you. So earlier I ignored KW, but I shouldn't have done that. And I'll tell you the reason I did that. The reason I ignored KW was one, it makes the calculation a lot more complicated. And two, KW's contribution's kind of insignificant. You know, KW, what's the most it can give? The most it can give is 10 to the minus 7, but it's going to give less than that because of the Le-Chatelier's principle. And so this is what we're going to see. I'll show you a calculation of this to show you what I'm talking about. So really, I should have taken this 6.616 and put it over here. And so we're going to do the same thing. We're going to have initial change equilibrium. Now, what I'm going to do is I'm going to take the hydronium here and bring it down into this, which I'll call step 2. So this is step 1. Step 1 is how much hydronium is produced from the ammonium. Well, that's going to be X. And that's where I'll start off here. H2O is a pure liquid. Now, the hydroxide, we're going to assume that nothing's happened yet. And then we're going to allow it to react. So we're going to lose some water, and we're going to gain some hydronium and some hydroxide. And so I'm going to call that Y. So for every 2 waters that react, I form 1 hydronium and 1 hydroxide. So that at equilibrium, at the end of this, I'm going to get X plus Y molar hydronium and then Y molar hydroxide. So X is the hydronium produced from step 1. Y is the hydronium produced from step 2. And that X plus Y will equal the total hydronium present in this mixture. And the total hydronium present in this mixture is the hydronium produced from the acid and the hydronium produced from water, KW. Okay, and that's what I should have equal here. This is the total hydronium, and that's got to go here. And so X plus Y is equal to 6.61 times 10 to the minus 6 molar. So I didn't bother doing this because this is 2 unknowns and 2 equations that I need to solve it. One equation would be this, the K value, which will be the hydronium times the ammonia divided by the ammonium. And so I plug the X's in here, whatever the values are. And then the second equation would be over here, that is K is equal to the hydronium times the hydroxide. And then I plug it in here and then solve. You know, when you have 2 equations, 2 unknowns, you solve for one and then substitute. Okay? So we solve for one and substitute and then figure out what x and y are. So I didn't bother doing step 2 because of this. I was expecting a negligible amount of hydronium. Why? I was expecting a negligible amount of hydronium because what happens if I add more hydronium? Le Chatelier's principle says if I have, let's say, Kw at equilibrium and I add more hydronium, it's going to shift the equilibrium to the left. If I add more hydronium to this, it shifts it to the left. Well, in this case, it's a little bit different because I'm not starting off at equilibrium. I'm just going to have the hydronium in there, and this is going to be Le Chatelier's inhibition, the forward reaction. If I already have a bunch of hydronium in here, I don't need a whole lot more to satisfy the equilibrium condition. And so what this is called is, it's the common ion effect. The common ion between step 1 and step 2 is hydronium. And if I have a bunch of hydronium already present here, then that's going to inhibit how much hydrolysis happens in the second step, how much reaction I get in the second step. And so I know if this were 0 and 0, I'd get 10 to the minus 7 and 10 to the minus 7. But since I already have some here, this is about maybe 10 to the minus 6, so I already have some here, then the amount I get from these are going to be more like 10 to the minus 8, 10 to the minus 9. A lot smaller because of the algebra. I don't need as much y here because I already have a bunch of x here to get it to equal this, to equal 1.0 times 10 to the minus 14. So the common ion effect inhibits the forward reaction because I already have product there. I don't need to form as much product. And so I went ahead and assumed this. I assumed the simplifying assumption. I assume that x plus y is about equal to, I assume that y is pretty much negligible. I don't expect much additional hydronium here, so x plus y is about equal to x. Well, if x plus y is about equal to x, then why not just stop at step 1? Plug that in here and then do the calculation. So that's what I did. But, you know, you being not as experienced, you need to go through all the steps. You know, I skipped this step, but that's because I knew it was going to be small. But I'm not going to do the math for this one. You know, instead, what we'll do is we'll do a repeat of the calculation in part 2 of the lab. In part 2 of the lab, we use the K value that we generated in part 1 to calculate the pH in part 2, the stoichiometry in part 2. So let's take a look at the part 2 of the lab. And in this case, I'm going to go through the full calculation. Because when you did the calculation, did you factor in the additional hydronium you would get from Kw? No, you didn't. But this time we will. And so here is part 2. We did ammonium, and we did a 1 to 2 dilution, so it came out to 0.05 molar. That was our initial. And then we had our water, H2O liquid. This is going to hydrolyze to form hydronium and ammonia. Okay, what was the K value that we calculated for this? Okay, that sounds good. This was the experimental K value that we got.
Yeah. If you want the...
No, that's fine. We'll just go with that. H2O is a pure liquid, and we're going to assume that nothing has hydrolyzed yet. Okay, we just mix this up. Now let it hydrolyze. The weak acid is partially hydrolyzed. Weak acid is partially hydrolyzed. We're going to have minus X molar plus X molar plus X molar. And so at equilibrium, I'm going to have 0.05 minus X molar. This is going to be X molar here. This is going to be X molar here. Okay, now we'll go ahead and solve this here. And you already solved this, right? What did you get for x? Or did you already solve it? Yeah, okay, what did you get for x?
4.668 times 10 to the negative 6.
Okay, that's for the hydronium. Okay, what was the ammonia concentration? It should be the same.
Yeah.
Oh, yeah.
And then that leaves us with the ammonium concentration. The ammonium concentration is going to be 0.05 minus point, only 5 zeros, 1, 2, 3, 4, 5, and then a 4, 6, 6, 8. Let's add some zeros here. And then we're going to get 0.04995332 molecule. And that's where we stopped, and we calculated the pH. What was the pH you calculated based on step 1 here?
5.35.
Yeah. So the pH came out to 5.33. That's good. But we made a little bit of an error. We made a little bit of an error because in pure water, in water, they're collisions. And the two water molecules can collide together to form some additional hydronium. Did we factor that in here? No, we didn't. We didn't. We could also double check our calculation. The way we could double check this is just recalculate K with these concentrations. Assume it's correct. So really, we shouldn't have stopped here. And I shouldn't have calculated the pH here. I need to know how much additional hydronium is formed from Kw. Okay, so we're going to call this step 1. And then over here will be step 2. Step 2 will be water collides with water. And so there's plenty of water around in this ammonium solution. And when water collides with water, it can result in some hydronium and some hydroxide form. Now this is not pure water. You know, there's some acid in here. And so what this means is this. There's going to be a common ion between step 1 and step 2. The common ion is hydronium. So we're going to take all this hydronium that was formed in step 1 and bring that into step 2 here. And so all that hydronium is 4.668. Times 10 to the minus 6 molar. Okay, so initially we put all that hydronium in here, water that's pure, so we ignore that. Hydroxide, we're going to say that none of the water has collided yet. Okay, this is called the common ion effect. What the common ion effect is going to do is it's going to inhibit, because normally we know in pure water we're going to get 10 to the minus 7 molar and 10 to the minus 7 molar. But if we have a common ion present there, we're going to get less than 10 to the minus 7 molar and 10 to the minus 7 molar. How much? I don't know how much less. And so what I'm going to do is I'm going to call that Y. So this is going to be plus Y and plus Y. And it's got to be less, otherwise the product is going to be too big. It's going to exceed K. Kw is 1 times 10 to the minus 14, 1.0 times 10 to the minus 14. So Kw, 1.0 times 10 to the minus 14. So at the end of this, I'm going to have 4.668 times 10 to the minus 6 plus Y molar, and then Y molar. So when I look at this binomial here, the first term is the hydronium from step 1. The second term, which is Y, will be the hydronium from step 2. The hydronium from step 2 will be the same as the hydroxide from step 2, because for every hydronium we produce in water auto self-reaction, we're going to produce 1 hydroxide. Okay, then we're going to plug it into this equation here. Kw is equal to the hydronium ion concentration at equilibrium times the hydroxide ion concentration at equilibrium. Now this is the total hydronium, because the total hydronium is going to be the hydronium from step 1, 4.668 times 10 to the minus 6, plus the hydronium from step 2, Y, times Y. Okay, this is a pretty simple quadratic. I can solve this, or I can try the simplifying assumption. I'm going to try the simplifying assumption because I don't expect much forward reaction here. This is 10 to the minus 14, which tells me it's all reactant, very little product. So if I try the simplifying assumption, which saves me a little bit of math, this is going to simplify to 4.668 times 10 to the minus 6 times Y. And then let's solve for Y. Y is equal to 1 times 10 to the minus 14 divided by 4.668 times 10 to the minus 6. And I get 2.14 times 10 to the minus 9. Okay, I need to justify the simplifying assumption. In order to justify it, we need to calculate the percent change. The percent change is going to be the change, Y, over the initial, 4.68. So that's going to be 2.14 times 10 to the minus 9 divided by 4.668 times 10 to the minus 6. Times 100. And this comes out to 0.04%. 0.045. Or about half, 0.05%. Is it okay? Yeah, it's okay. In fact, let's take a look here. So if I calculate the total hydronium is going to be in decimal form. So this is, I'm going to put 5 zeros. 1, 2, 3, 4, 5, 4, 6, 6, 8. Plus, so that's the hydronium from the ammonium. Let's calculate the hydronium from Kw. I'm going to need 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then a 2, 1, 4. And then let's go ahead and total it up. It's going to be 0.00000, 5 zeros of 4, 6, and then 2, and that will be 7. So I went from 4668 to 4670. You know, I got a little bit more hydronium. Do you see that? In step 2. Okay, let's go ahead and calculate the pH now. So I'm going to type that in 0.0000467 log negative. And do you know what the pH comes out to? 5.330. 5.330. Did it make any difference? What was the pH? If we skip step 2 entirely, the pH is 5.33, the pH is 5.33. You see? And so the situation here is This, you know, when we're dealing with 10 to the minus 6, and then we add 10 to the minus 9 to it, that's 3 orders of magnitude lower. 10 to the minus 6 to 10 to the minus 9, 1,000 times smaller. And what that means is it's going to have a negligible impact on it. And so this is why I skipped it. I skipped it because of the common ion effect here. And so it depends on how much hydronium you have. If after step 1, let's say if after step 1 I had 10 to the minus 9 molar hydronium, then do you think water might be significant? Yes, it would be significant. Likely. If after step 1 I have 1 molar hydronium, if I have 1 molar hydronium, do you think Kw is going to be significant? No, because what's the most Kw can give you? Kw, the most it can give you is 10 to the minus 7 molar. And so we don't worry about it too much. So the pH scale is going to look something like this. In the middle, we'll have pH 7, which is neutral. And then as we go up, this is what we call basic, to about 14 and then higher. And so this would be strongly basic, moderately basic, weakly basic. Now, if I have 1.0 molar sodium hydroxide, that's going to give me 1.0 molar hydroxide. If I have 1.0 molar hydroxide, am I going to worry about the tiny bit of extra hydroxide I get from Kw? What's the most I'm going to get? The most I'm going to get is 10 to the minus 7 molar. Will adding 10 to the minus 7, 1 times 10 to the minus 7 molar to this make any impact at all? No. I mean, if I did, the most I'd get is 10 to the minus 7, so that's 6 zeros and a 1. But because of the common ion effect, I'm going to get a lot less. And so if I get a lot less, it has really no impact on that. And so here we ignore it. And so when we do this, this is what we'll do. We'll get the, I should do the relationships with the calculation. Let me do this. Yeah. We'll get something like this. Now, Kw always holds, whether it's pure water, an acid, or base solution. The hydronium and hydroxide will be in a seesaw relationship. It's always going to equal 1.0 times 10 minus 14 at 25. So if the hydroxide shoots up, the hydronium must shoot down. And so if we have this, then this would be equivalent to 1.0 times 10 to the 0 molar hydroxide. And when I look at the power of the hydroxide ion concentration, the power of the hydroxide ion concentration is going to be 0. That would be the power. If I have the power of the hydroxide ion concentration, then there's some relationships that come up here. And this is relationships dealing with log. And so the pH, if I wanted to calculate it, is the negative log of the hydronium ion concentration, or the hydrogen ion concentration. And the pOH is the negative log of the hydroxide ion concentration. And it turns out that the pH plus the pOH is equal to the pKw, the power of Kw. The power of Kw is 14. So this is going to be 14, and then I have 2 sig figs, so 14.00. So there's going to be the seesaw relationship. So if the pOH is 0, then that means the pH is 14. And I have 2 sig figs here, so I'll go 14.00. If the pH is 14.0, then that means the hydrogen ion concentration is 1.0 times 10 to the negative 14 molar. And so, in other words, it was significantly reduced by having all this hydroxide present. And, so. Okay, on the other end of the spectrum, we have acidic solutions. And so over here, we'll have weakly acidic, moderately acidic, and strongly acidic. Strongly acidic will have, pHs of 0 or less. So we get an idea if we can ignore Kw or not. I have a strong base there, I can probably ignore it. I have a strong acid here, 6.0 molar HCl. What would the pH be for this? If I have 6.0 molar, do you think Kw is going to contribute much? The most Kw can contribute would be in pure water, which would be 10 to the minus 7. It's going to contribute a lot less than 10 to the minus 7 molar. And so when I look at the pH here, the pH is going to be the negative log of the H plus concentration. The H plus concentration in this case is going to be 6.0. And so what is the pH? It's very small. Okay, what would the pOH be? Yeah, 14.778. The pH and the pOH have to add up to 14. And that means the hydroxide ion concentration would be very low. The hydroxide ion concentration is going to be 10 to the minus 14.778, which is between 10 to the minus 14 and 10 to the minus 15. The hydroxide ion concentration comes from water. And the hydroxide ion concentration would equal the hydronium ion concentration that comes from water. And so the contribution of hydronium from water would be about 10 to the minus 14, 10 to the minus 15. 10 to the minus 14, 10 to the minus 15 is going to have no impact on 6. It's negligible. Okay, what is the pH of 1.0 times 10 to the minus 8 molar HCl? Well, HCl is a strong acid. Does a strong acids ionize or dissociate or hydrolyze completely? So if I have this, then what that means is I'm going to have 1.0 times 10 to the minus 8 molar H plus, which is the same as hydronium. And so what's the power of the hydrogen ion concentration here? The power of the hydrogen ion concentration is the exponent here, which is 8. And the number of sig figs, I have 2 sig figs here. Power functions, the sig figs are after the decimal. So I have 2 sig figs here. I'll have 2 sig figs here. So the pH is 8. A pH of 8, what would you guess? Weakly acidic, moderately acidic, or strongly acidic? Should be weakly acidic. So pH of 8 is weakly acidic. Is that correct? So we look at the pH scale. And so we're at 7, and so we're just slightly above 7. We're at 8, and so pH 8 should be weakly acidic. And pH of 14 should be strongly acidic. Is that All right, pH 14 is strongly acidic and all right, so pH of 14 is strongly basic, and that means a pH of 8 must be neutral, and a pH of 7 must be weakly acidic. Is that right?
Is it 7?
Well, oh yeah, 7 is neutral. So this is not weakly acidic. This must be weakly basic. Weakly basic. So 1.0 times 10 to the minus 8 molar hydrochloric acid must be weakly basic. And therefore HCl is a weak base. Is that right? HCl is a weak base because it makes a weakly basic solution. Does that sound right to you? No, actually HCl, is it a weak acid or strong acid? How sure are you that it's a strong acid if it's giving you a pH of 8? Or how sure are you that pH of 8 is actually basic and not acidic? Yeah, well, this is a strong acid. It's a strong acid on the acid-base chart. You're right. It's a strong acid. So why is a strong acid giving us a basic solution? It doesn't make sense. And the reason is simple for this case. When we have very little hydronium, 10 to the minus 8, will water, Kw, be a significant contributor to the hydronium? And the answer is yes. If we have a little bit of hydronium, then we got to worry about water because water is going to give us a little bit extra hydronium. And so if we already have a little bit, then a little bit extra is significant. If we have a lot, then a little bit extra is insignificant. So it depends on how much hydronium I have from the first step. If I have a lot of hydronium, then I don't worry about the little bit I'm going to get from Kw. But if I have a little bit of hydronium, then I'm going to worry about the little bit I get because I only have a little bit. Does that make sense? And so in this particular case, our assumption failed. The assumption that I could ignore the second step failed because in this calculation, I have to do the second step. Otherwise, it's not going to work. I'm going to get the wrong answer. And so what I'm going to do is I'm going to stop here. And then we're going to do this calculation next time. I'll show you. It's not a difficult calculation, and then we'll get a number that looks reasonable, a number that's acidic and not basic. Okay. And it turns out that hydronium from water is a very significant contributor here. In fact, we get more hydronium from water than we do from the acid because we have so little acid present. This reminds me, you know, in high school chemistry, my high school chemistry teacher would always say, you know, if you take hydrochloric acid and sodium hydroxide, mix them together, you get salt, sodium chloride, and water. And so he said, you know, you could drink this stuff. So all semester I was waiting for him to drink it, but he never did. But you know, we drink this all the time. There's so little HCl in there, you know, it's like, I drink it without neutralizing it, you know, because it's so dilute. And we'll see that soon, tomorrow. In fact, you drink more acidic water than this if you drink it from there. Do you know what the pH of this water is? The pH of this water is like 5. Even our deionized water, the pH is a little lower than... Our deionized water is not pH 7. Yeah. Okay. All right, I'm going to stop here, but today we're going to check our crystals, right? And then we're going to see, hopefully we have crystals. If we don't have crystals, then we're going to do a couple of extra steps to get crystals. But hopefully you have some nice crystals there. And then what we're going to do is we're going to filter those using the Buchner funnel. You have to check that out and vacuum. And then we're going to wash the crystals, and then we're going to take about half those crystals and then recrystallize them. Recrystallizing them means dissolving them in a minimum of water and then adding a little bit of alcohol If you add the alcohol and you get a whole bunch of crystals form again, then that's not good. You know, we want to minimize nucleation, maximize growth. Okay. So if there are any questions, let me know, but otherwise we'll get started. So take a look at your crystals.